This film describes an electroacoustic coupling mechanism implemented using an ionized plasma gas. An electroacoustic coupling mechanism has its most familiar form in the shape of a hi-fi loudspeaker, where magnetic fields generated by a time-varying current oscillate a magnet attached to a cone. The oscillations cause displacement in the air at the cone face, producing pressure waves which travel as sound. The same effect can be achieved by replacing the mechanical driver with a plasma gas. Due to its conductive nature, the charged particles in such a gas respond readily to the changing electric field. Through collisions between the charged particles and the surrounding air molecules, pressure waves can be generated within and around the plasma column. The effect is similar to a lightning strike. A current flows in a narrow channel in air, causing ionization through collisions between the charged particles and the air molecules. The time-varying field causes electrons to gain energy, which is transferred most efficiently through inelastic collisions to the internal vibrational states of the air molecules. The comparable mass of vibrationally excited molecules and surrounding neutral gas molecules provides an efficient coupling for further transfer of energy through elastic collisions. This increases the energy of the neutral gas molecules and the temperature of the gas in the column as a whole. With the heat contained within the column, thermal expansion occurs where the internal dimensions of the ionized column rapidly expand and contract. This expansion causes pressure variations external to the column, which propagate as sound waves. The plasma used here is electrically generated in air at atmospheric pressure. The dielectric strength, or breakdown in dry air, is approximately 3 kilovolts per millimetre. So for the 15 millimetre electrode separation used here for this plasma, a voltage drop of up to 45 kilovolts is required to initiate breakdown. Such voltage levels can be achieved through the use of a resonant transformer like this solid-state Tesla coil. For the solid-state version, the familiar spark gap and capacitance combination of a traditional Tesla coil has been replaced with a high-power inverter circuit. The resonant frequency is determined by the capacitance and inductances of the coil, and for the circuit values here is approximately 325 kHz. The inverter circuit contains 4 MOSFET transistors in an H-bridge configuration. A control stage provides a logic signal that alternately switches the transistors, chopping the input DC signal. The output signal is a high current alternating square wave with the same voltage amplitude as the input signal. Due to its resonant nature, the circuit picks out the fundamental frequency of the square wave, with the sinusoidal AC current in the primary generating an induced voltage across the electrodes high enough to achieve breakdown in air. The inductor in series from the DC power supply acts as a choke, protecting the supply from the back EMF signals generated by the Tesla coil. An increase in the input DC voltage corresponds to an increase in the power to the plasma and leads to higher rates of excitation and ionization in the gas molecules. As will be seen here, this is reflected in the increased optical emission resulting from relaxation of the excited molecular states. In its unmodulated state, the plasma can be represented as an equivalent electrical circuit with a capacitor and resistor in parallel. Pre-breakdown, the circuit will be purely capacitive, and the circuit is dominated by the displacement current. Upon breakdown, the plasma behaves as a nonlinear resistor through which a conduction current flows. The total current then contains capacitive and resistive components. The voltage across the plasma is monitored using this high voltage probe. The current is monitored across a resistor from the top electrode to ground, and both the current and voltage waveforms can be seen on this oscilloscope. As I increase the DC voltage into the coil, you can see a corresponding increase in the voltage at the top electrodes. In its pre-breakdown state, the voltage is a little above 20 kilovolts. Post-breakdown, the plasma is sustained at a peak-to-peak voltage of approximately 5 kilovolts on a continuous RF cycle of 325 kilohertz. The corresponding conduction current is 30 milliamps. An audio signal is applied across the DC supply into the power stage. When switched on, the signal varies the amplitude of the higher resonant frequency signal and an amplitude-modulated excitation is generated. The capacitor connected in series with the audio amplifier acts as a high-pass filter, protecting the audio source from the DC signal of the power supply. To test the acoustic response of the plasma, several audio frequency signals will now be applied to the Tesla coil. For this, I use a signal generator, which is connected to a standard audio amplifier, the output of which is connected across the DC power supply. Plotting the sound pressure level gives an indication of the frequency response of a source. The sound pressure level is a logarithmic measure of the RMS sound pressure generated by a source relative to a reference value, which here is 20 micropascals. For reference, the sound pressure level from a television at half volume, measured at a distance of around 1 meter, is around 55 to 60 dB. For the plasma, a constant sound pressure level of 65 dB at high frequencies drops off sharply below 3 kHz to around 45 dB at the lowest measured frequency of 300 Hz. Additional measurements made in an anechoic chamber confirm this trend and gives a fuller picture of the broadband frequency response. There are a number of reasons for the limited low frequency response measured here. The pressure level generated from a source is dependent on the volume of air that is displaced at its surface. The plot here shows the required volume displacement as a function of frequency to achieve a sound pressure level of 94 dB at a distance of 1 meter. It can be seen that to maintain a constant pressure amplitude, an increasing volume of air needs to be displaced as the frequency decreases. A conventional loudspeaker utilizes several appropriate diameter cones combined with appropriate crossover filters to produce a near broadband emission. A large diameter cone displaces a larger volume to achieve sufficient bass response. Due to a small surface area, the plasma is limited in the amount of air that can be displaced, which impacts on the low frequency response. In addition to its size, effects within the plasma can also limit the frequency response. At high modulation frequencies, the relaxation time for thermal diffusion in the gas is much greater than the time taken for the energy transfer from the electrons to the gas molecules. The heat is contained within the plasma, leading to thermal expansion and sound emission. As the modulating frequency decreases, the relaxation time for diffusion becomes comparable to the energy transfer process, so that in the time taken for energy transfer between charged particle to the neutral gas molecule, energy or heat will diffuse out of the column. No rapid thermal expansion occurs, pressure equilibrium is maintained, and in turn, no sound emission occurs. Finally, the response of a more complex signal will now be demonstrated. I've replaced the signal generator with this keyboard, and by playing a tune, I can demonstrate the system's response to a combination of signals of different amplitude, frequency, and phase. Although the plasma has its limitations, the higher frequency response indicates its potential as a tweeter speaker, which when coupled with a lower frequency bass speaker can provide a broadband source efficiently coupled to air,